Hello, my darlings. All right, today we're going to look at part 2 of the Fundamental Theorem of Calculus. We're finally going to make it to part 2. So let's start with this assumption. We're going to let f be any antiderivative of the function f. Now, that being said, I also want to let this capital F of x be the function g of x plus c. So now, if I want to find out the value of f of b minus f of a, that would be the same as the value of g of b plus c minus g of a plus c, right? All I did is change from f's to g's. So now notice also here, see this plus c, and then this negative is going to come over to this plus c, and what's going to happen? They're going to add to 0. So all I'm going to be left with is g of b minus g of a. So in other words, it doesn't matter what this constant is. Now we're going to use here the definition of an antiderivative. And if g of b is an antiderivative of little f, then that means it's the integral from a to b of f of t dt minus g of a is going to be the integral from a to a of f of t dt. Okay, now if we look at this, I'm going to keep this first integral from a to b of f of t dt minus, but take a look here. What do we know the value of this integral is? If we're going from a to a, we've gone nowhere, right? And there's no area, and the value of the integral is 0. So that means this just becomes the integral from a to b of f of t dt. Well, do you realize what we just said? We went from here to here. So what that means is that the integral from a to b of f of t dt is the antiderivative capital F evaluated at the upper limit b minus the antiderivative f evaluated at the lower limit a. And that is the Fundamental Theorem of Calculus Part 2. So if f is continuous at every point in the closed interval from a to b, so it has to be continuous. Continuity is so important. And if f is an antiderivative of the function little f on that closed interval, then the integral from a to b of f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. And this part of the fundamental theorem is also called integral evaluation theorem. Okay? Now it also goes on to tell us that any definite integral of any continuous function f can be calculated without taking limits, without calculating Riemann sums, and often without much effort, as long as an antiderivative of f can be found. No way. Without much effort? Without rectangles or trapezoids? Let's see. So here we go. Here's the integral from 0 to 1 of x squared minus 2x plus 3 dx. Now the first step is to find the antiderivative. So I'm going to open up square brackets here. The antiderivative of x squared is x to the third divided by 3 minus the antiderivative of 2x would be x squared plus the antiderivative of 3 is 3x plus, we always put a constant on our antiderivatives, right? And then notice now this is a straight up and down because this is a such that the x's are evaluated from 0 to 1 because we're still on that integral. Now that's a straight up and down line. That's our such that. That's how we're going to know. We're going to plug in. Now here's step 2. Step 2 is we evaluate the antiderivative at the upper limit minus the antiderivative at the lower limit. So we're going to take 1 first. 1 cubed over 3 minus 1 squared is 1, plus 3 times 1 is 3, plus c. And then we're going to take this lower limit and plug it in. And we're going to have 0 thirds minus 0 plus c. Okay, so what is that going to give me here? I have 1/3 plus 2 plus c minus c, right? Well, 1/3 plus 2 would be 6/3, so that's 7/3. And look at this c and the minus c. They're going to add to 0, right? Regardless of where we're evaluating from. This c, and we're always going to have a minus between the antiderivative at the upper limit and the antiderivative at the lower limit, means we're going to have a minus c over there. So my question to you, is the plus c necessary in this situation? No. If you have definite integrals. Now a definite integral means the lower limit and the upper limit are both numerical values. If we have a definite integral, the arbitrary constant is not necessary. Is not needed. Yay! One less thing to have to write. All right, let's try another one. So here we go. We're going to do the integral from -2 to -1 of 2 over x squared dx. Now the first thing I would suggest, rewrite this as 2 times x to what exponent? -2. That's right, the negative will bring it out of the denominator. Now we're ready for our antiderivative. I'm going to keep the 2. When I add 1 to my exponent, that's a -1. And if I divide by -1, that's going to make that -2. And I have to evaluate this from -2 to -1. Now remember, this is really -2 over x, if that's easier for you to work with. Whatever's easiest. Now we're going to plug in the upper limit first. So that's -2 over -1 minus, now we're going to plug in the lower limit, so we're going to have -2 over -2. Well, what's that going to give us? -2 divided by -1 is 2, minus -2 divided by -2 is 1, so we're going to get 1. All done. All right. Look, oh, we got a trig one. I know how much you love trig. Let's do it. It's not that bad, I promise. What's the antiderivative of 1? What has a derivative of 1? That would be x. And notice the dx is telling us, remember, what the variable is. Plus, what has a derivative of cosine x? That's sine x. And we're going to evaluate this from 0 to pi. So the first thing we do is we plug in the top limit, pi plus sine pi, minus, now we're going to substitute in the lower limit, 0 plus sine 0. So let's see, that gives us pi plus, now remember, your sine of pi is 0, minus 0 plus sine of 0 is also 0. So all we're going to get here is pi. The value of the integral is pi. All done. Here's another one, and again, it's trig. We're going to do the integral from pi over 6 to 5 pi over 6 of cosecant squared x dx. Now, what has an antiderivative of cosecant squared? Well, it's not quite cotangent x, it's the negation of cotan x. And we have to evaluate this from pi over 6 to 5 pi over 6. Okay, so that we plug in the top number first, so it's the negative cotangent of 5 pi over 6 minus, now we're going to take the negative cotangent of pi over 6. Now remember, guys, pi over 6, in case you're stuck on degrees, pi over 6 is 30 degrees. 5 pi over 6 is 180 minus 30 degrees. That's 150 degrees. Okay. Now, we've got this negative, so I'm going to bring that down. Cotangent's the reciprocal of tangent, right? So 150 degrees is in quadrant 2. So think about this. 150 is here. Quadrant 2, all students take calculus. Tangent is negative in that quadrant. The reference angle is 30 degrees. The tangent of 30 degrees is radical 3 over 3, But we have the cotangent, so we take the reciprocal. So we have the negation of negative 3 over radical 3. Whew, a lot of trig there. Plus, now we need the cotangent of pi over 6, or just the cotangent of 30 degrees. Well, we just said that the tangent of 30 degrees is rad 3 over 3, so the reciprocal is 3 over radical 3. Now remember, two negatives, that gives you a positive. 3 plus 3 is 6, and we keep the common denominator. This answer is perfect. Please do not get upset if you happen to look at a textbook or an answer key somewhere and you don't have the same answer, because they may have used a rationalized form. Maybe they knew their tangent as 1 over radical 3 instead of radical 3 over 3. Doesn't mean you're wrong. Look to see if it's equivalent, because if their answer was 2 radical 3, that happens to be exactly the same as yours. Both answers are perfect. So if it's multiple choice, just make sure yours is an equivalent. Check and see if you have to rationalize it, okay? All right, now let's do another one. Now this one's a little different. Now first off, there's u's, but notice we're taking the derivatives u's. So it would be just like doing the integral from 9 to 4 of 1 minus the square root of x over the square root of x dx. Don't let the letter bother you. However, do you know what has an antiderivative of 1 minus radical u over radical u? Heck no. But if we undo the subtraction that's in that numerator, we would have 1 over the square root of u minus the square root of u over the square root of u, right? Isn't that what came before that? Now we can simplify that a little bit. So what we're doing is we're undoing the subtraction, and now we've got the integral from 9 to 4 of, now we have 1 over the square root of u. The square root of u is u to the 1/2, but since it's in the denominator, we raise it to the negative 1/2. Minus the square root of u over the square root of u is 1 du. Now, I also want to make note here, this is an integral going from 9 to 4. And up to this point in our calculus that we've done so far, we always had to have the lower limit first. We don't have to do that. That was because we were finding the areas from the graphs and we read left from right. And if we went backwards, we had to negate it. If we leave this limit in order, it'll be okay, because if we know the antiderivative, let's say the antiderivative is capital F, f of 4 minus f of 9 is the negation of f of 9 minus f of 4. So it's still going to be, it would be just like switching the limits and negating the integral to have them in the right order, but I don't have to since I'm actually doing it numerically. So it's actually less work. Okay, let's do our antiderivative now. What has a derivative of u to the negative 1/2? We add 1 to negative 1/2, that's 1/2. When we divide by 1/2, that's like multiplying by 2. Minus what has a derivative of 1, that's u, evaluated from 9 to 4. So also think about this. Remember, this is 2, and u to the 1/2 is the square root of u, minus u, from 9 to 4. And yes, you can skip that step if you want, that's fine. We're going to substitute in our upper limit. Notice it's not the bigger number, that's okay. 2 times the square root of 4 minus 4. Then we're going to minus, and we're going to plug the 9 into our antiderivative. So 2 times the square root of 9 minus 9. Now we've got 2 times 2 minus 4 minus 2 times 3 minus 9. So this is going to give us 4 minus 4, which is 0. This is going to give us 6 minus 9, which is a negative 3. So we have 0 minus a negative 3. That's positive 3, and we're done. Awesome. Now, I have another example that I want to take a look at. I want to find the area bounded by the curve y equals x squared minus 2x and the x-axis. X equals negative 1 and x equals 2. So I'm going to look on the graph. Here's where x is negative 1. Here's where x is 2, and if I have x squared minus 2x, this is y equals x times x minus 2, which means my roots are at 2 and at 0. And if I plug negative 1 in there, that's 1 plus 2, that should be 3. And if I plug a positive 1 in there, that's negative 1. So this is my piece of the parabola that I have. Whoops. My piece of the parabola that I have. Now, I want the area that's here and here. There's a problem, though. I want area, not just the integral, because the integral is going to make this positive, but it's going to make this area negative. I'm not asking for the signed area or the net area. I want the actual area. So in order to do that, our area is, we can take the integral from negative 1 to 0, because that's where the function is positive or 0, of our x squared minus 2x dx, but then we have to subtract the integral of the part of the function that's below the x-axis. So the integral from 0 to 2 of x squared minus 2x dx. All right, we're ready to go. And I'm going to put brackets here. Now the antiderivative of x squared is x cubed over 3 minus the antiderivative of 2x is x squared. And we're going to evaluate from this from negative 1 to 0. Minus, now notice in this next integral, the antiderivative is exactly the same, but our limits are now from 0 to 2. Okay, so we're going to substitute 0 into this first part. So we're going to have 0 minus 0. That's easy. Minus, now we're going to plug negative 1 in, and we're going to have negative 1/3 minus 1. But also notice all of this is from the first integral. Minus, then we're going to have to do another set of brackets for the second integral. And we're going to substitute in the 2 first. So 2 cubed is 8 over 3 minus 2 squared is 4. Then we're going to subtract, and we're going to substitute in the 0. So we'll have 0/3, which is 0, minus 0. All right, now what do we have here? So this all is 0. We have the negation of negative 1/3 minus 1. That's a negative 4/3, so this makes it positive 4/3 minus, and then we have 8/3 minus 4/3. Now 4/3 is 12/3, so 8 minus 12 is a negative 4/3, but 2 negatives makes a positive, and now we have 8/3 is the area. So 8/3 is the actual area. Awesome. Now just a couple things here. If you're finding the total area analytically, okay, you want to find the area between the graph of y equals f of x and the x-axis over the interval from a to b. Partition the interval where the zeros were, just like we were here. We found the zeros were at 0 and 2. We broke it up into 2 integrals, from the start to the 0, from the 0 to the end. So we partition it. We integrate f over each subinterval. Okay, we can add the absolute values of the integrals, or we can subtract the negative. It's the same thing. Another way to do this, if you're doing it numerically, which means with your calculator, okay, you can find the integral from a to b of the absolute value of f of x dx using your calculator. Okay, so you can use the integral from a to b of the absolute value of f of x dx. That will give you the total area. That will give you the total area. So in other words, if we went back to this problem and we went to our TI-Nspire, we could type in the integral from negative 1 to 2 of the absolute value of x squared minus 2x dx, and it should give us this same answer of 8/3. Let's go take a quick check on our calculator. Okay, so we're on our calculator page. We're going to use our template key, and we have the integral. We're going from negative 1, tab up to 2, tab over. We're going to go back to our template key. This time we want the absolute value, which is right above it. Click enter. Our function was x squared minus 2x. Tab out of the absolute value, tab over. So we can say dx, press enter. There we go. We have 2.666665657. Let's make sure if I do 8 divided by 3, because that's the answer we got, right? And I'm going to put a decimal. And there it is, same fraction. Now notice it's slightly off. That's because the calculator is actually doing Riemann sums. When it's doing an integral, it's actually computing with a lot of Riemann sums, a lot of rectangles. Okay, so sometimes it's slightly off, but that's why we round to 3 digits after the decimal and not 10 digits after the decimal, because it's not perfect. All right, guys, so we just learned the second part of the fundamental theorem of calculus. We now know that when we have the integral, we can take the antiderivative, evaluate it at the upper limit, minus evaluate the antiderivative at the lower limit. Have a great day, guys. Bye.